In this video, we'll learn how to graph exponential and logarithmic functions that have transformations. Now, before we begin graphing these, let's review our knowledge of a, b, h, and k. What you are going to notice in this particular set of equations is that the base of my log and the base of my exponent, because they're typically denoted with a b, I put these with a capital B to denote that they're the base of the log or the base of the exponent, and they aren't related to a, b, h, and k that are typically used in our transformations. So you'll notice that a multiplication out in front is still going to be where your vertical stretch and shrink and your flip occur. So this is still vertical stretch, shrink, and flip. And because it's a multiplication on the outside, it's a multiplication to your y values. Then from here, we have our b values. Remember, these are your horizontal, and then we have stretch, shrink, and flip. So I'm using the same words from over here. So b is our horizontal stretch, shrink, and flip. It's a multiplication to our x values, but remember that it gets flipped to its reciprocal. So we multiply by 1 over b. So we have A, that's our vertical stretch, shrink, and flip. B, that's our horizontal stretch, shrink, and flip. And it will actually be 1 over B, which is the reciprocal, as we apply that transformation for B. Then from here, we have our K values. I'm going to do these ones on the outside first. This is a translation, which means it moves it up and down. So it's a translation up and down, and it works just as expected. And then our k value is going to be there with x, and this is your translation that is left and right. And remember that this one, we put the subtraction sign in here to remind you that it works the opposite of what we expect. Now, a couple of things to note, because these are functions we haven't done transformations with before. You'll notice that b and h are either up here in the exponent with x, or they are inside of the logarithm with x. So that's how you denote the difference between a and b and h and k, because b and h are going to be inside either the exponent or the log with x, and a and k are always on the outside of the entire function. That's why b and h get applied to x, and a and k get applied to y. So hopefully you're remembering your transformation rules from previously, and we're going to apply those exact same transformation rules to these new functions we've been studying here in this unit. So let's jump in and look at our first example. What I notice when I look here at y equals -3 times 2 to the power of 1/2 x minus 1 and then all plus 4 is I have values for a, b, h, and k. So I have all 4 transformations up there in my exponential function. Now what I'm going to do to start is I'm just going to focus on the basic function, which is essentially just y equals my base here, which is 2 to the power of x. And I'm going to start by creating a table for that basic function, and then I'm going to apply a and b, which are the multiplication ones, then apply h and k, which are the addition subtraction ones, and then from there I'll create my graph. So let's start by creating a table of values for just the basic y equals 2 to the power of x, because 2 is the base of my exponent. That's not representing a, b, h, or k. So basically we've removed a, b, h, and k to make a basic graph that we can transform. So let's start with our -2, -1, 0, 1, and 2. You can use your calculator or you can use your exponent properties to find the y coordinates for these. If we plug in -2, we'll get a y value of 1/4 or 0.25, depending on which method you choose. Then here we'll get a value of 1/2 or 0.5, which they're the same thing again. Then with x is 0, we'll get 1, x is 1, we'll get 2, and x is 2, we will get 4. So that is where we start. I'm going to keep my fraction answers, but again, remember, if you have the decimal answers, that is fine too. So that is what we start with. Now from here, what we're going to do is we're going to apply a and b first, because multiplication comes before addition and A and B are transformations that are taking place using multiplication. Now remember, our A transformation is going to happen over here to Y. So we're going to take all of our Y values because A is a vertical stretch, and so that's going to change the Y coordinates, and we're going to multiply them all by -3. Then for my B value, which is 1/2, remember we flip B to its reciprocal, which is 2/1 or 2, and this is going to happen to our X variables because it's a horizontal transformation, and we're going to multiply all of these values by 2. So we're going to multiply all of those by 2 because 2 is the reciprocal of 1/2. So if I apply those transformations, what I notice here is that my X values become -4, -2, 0, 2, and 4, and my Y values become -3/4 or -0.75. Then we have -3/2, which is -1.5. Then we have -3, -6, and -12. So now from here, now that we've applied our A and B, now we're going to apply our H and our K. Now remember, K happens to the Y coordinates because it's a movement up and down. So for all of these, we're going to add 4. And then our H value, we take the opposite of that because H works the opposite of what we expect. We're going to add 1 to it, and that will result in a movement to the right. And that happens to the X values because it's a horizontal change. So here we create one last table of values. So if we add 1 to all of our X values, we get -3, -1, 1, 3, and 5. And then for our Y values, if you don't like adding fractions with integers, you can just convert these over to -0.75 and then -1.5. So then as we add 4 to those, we end up with 3.25, 2.5, 1, -2, and -8. So now we're pretty much ready to graph as we have this final table of points with all of our transformations in it. The last thing that we want to add in here is we want to talk about our horizontal asymptote. If you remember before, our horizontal asymptote was at 0. That's where it was. However, with all these transformations, this horizontal asymptote, or that imaginary line that we can't cross, has actually moved, and it actually has a new location. So it's no longer at 0. It has actually moved up 4 units. So if you look here at your K value is what actually shifts things all around. And so shifting your graph left and right doesn't change this horizontal asymptote because it would just stay right here at 0. However, that K value moving the whole graph up results in the horizontal asymptote moving up 4. So before you draw your new graph, you always want to find where your new horizontal asymptote is. And for the exponential graphs, it's all based on your K value. So because it's a horizontal asymptote, it's going to be moving up and down because it's a horizontal line. Moving it horizontally won't really change where it is, but moving it vertically will change its location. So if we move our horizontal asymptote up 1, 2, 3, 4, at y equals 4 up here is where the new line is that we cannot cross. So I always suggest drawing that in first so that you know exactly where that line is that you can't cross. So now let's plot our points. We have x is -3, y is 3.25, x is -1, y is 2.5, x is 1, y is 1, x is 3, y is -2, and x is 5, y is -8. So if we count 1, 2, 3, 4, 5. There we go. So you can now see our exponential function has been vertically stretched, horizontally stretched, moved to the right one, and then moved up 4. The last thing we need to do is find our domain and range. If we look carefully, our graph is going forever left and right. So our domain is all real numbers. And our range now starts at this 4 value. And our range are all of the y values that are less than 4. So now that we've seen an exponential example, let's jump in and try a logarithmic one. So here we can see we have values of a, b, h, and k. So I can see that those changes are going to take place. But to start, let's start with the most basic version of this logarithmic function with no a, b, h, and k. So we have y equals log of base 2 of x. So let's start there. Let's get a table of values for that function, and then we can use our transformations to actually transform that particular function. So remember, when we graph our logarithmic functions, we actually use the inverse function to help us, because creating a table of values for log base 2 of x can be a little bit tricky. So here, let's start with our inverse function to help us so that we can get a table of values for the logarithmic function. So we start with our inverse. We do x equals log base 2 of y. We then rewrite it into an exponential because that's how we find our inverse. So we have y equals, then we take our base, which is 2 to the power of x. So if we can find the table of y equals 2 to the power of x, we can then find our table for our logarithm. So let's start there with our inverse table. So we have x and y here. So if we do x is negative 2, y is all the way to 2, there we go. So now if we plug in these values, we find that our y values are 1/4, 1/2, 1, 2, and 4. And again, you can have the decimal versions of 1/4 and 1/2 as well. For 1/4, it would be 0.25, and for 1/2, it would be 0.5. So we can now use the fact that this is all of the inverse function information to create a graph for our logarithmic function. So that's what I'm going to do here. Remember, because they are inverses, all we need to do is we need to switch x and y. So here we can go over and we can switch x and y. So we have 1/4, 1/2, 1, 2, and 4. So now from here, we have our y values of negative 2, negative 1, 0, 1, and 2. Okay? So now from here, we can apply our a and our b values, because those are the transformations that require multiplication. Remember, a happens to y because that's happening to our vertical change. So we're going to multiply all of our y values here by negative 2. Then from here, we're going to multiply our x values by taking the reciprocal here. So this takes the reciprocal of 2, which is 1/2. So we're going to multiply all of these by 1/2. So as we do that, we end up with, that becomes 1/4 becomes 1/8. So if you want the decimal version, that's 0.125. 1/2, which was 0.5, becomes 0.25, which is 1/4. This 1 becomes 0.5, 2 becomes 1, and 4 becomes 2. So you can see that it shrunk down there. Then from here, we're going to multiply the y values by negative 2. So we have 4, 2, 0, negative 2, and negative 4. So we've applied a and b. Now the last things we're going to apply are h and k. Remember, h works opposite of what we expect. That means we're subtracting 3 here from all of the x values, and k is going to move the whole graph down. So we're going to be subtracting 1. So from here, if we actually apply those transformations, we end up with negative 2.875, negative 2.75, negative 2.5, negative 2, and negative 1. And then here, if we subtract 1, we end up with 3, 1, negative 1, negative 3, and negative 5. So this is our table of values that represents this logarithmic function right here with all of its transformations. So again, note with this particular set of transformations, we had to start with the inverse function to get points for that logarithmic function, and then we applied all of our transformations. So it takes a little bit more time. Now from here, the thing we have to keep in mind with logarithmic functions is, remember, logarithmic functions had a vertical asymptote right here. So it was the opposite of an exponential. An exponential had a horizontal asymptote. A logarithmic function had a vertical asymptote. So here we need to notice if this vertical asymptote moved left and right in any way. Well, h applied a -3 to all of our points. Because h works the opposite of what we expect, it moved it left 3. Since all the points on our graph moved left 3, this vertical asymptote also moved to the left 3 and has a new location here. So this is the imaginary line that our logarithmic function will not cross. We have to keep that in mind as we create our function. So let's go ahead and now start plotting these points. So if we go to x is -2.875, that's going to be up at 3. So it's going to be pretty close here to the asymptote. Then we're at x is -2.75, and it's at 1. So again, not moving very far. -2.5, it's at -1. So it's really, really steep here. Then at -2, it's -3. -1, it's -5. So it finally starts to curve up a little bit here. We can see that, and we can assume it's going to eventually curve up on that end and get really, really, really flat on this end. So we can see we have our logarithmic function that has that vertical asymptote at x equals -3. Now this graph is pretty flat. Most of the ones you'll see will start to grow a little bit sooner, but you can see that this one started creeping up as it got more and more negative in the y range. Now from here we have to find our domain and our range. Note that our domain has now changed. We need all of the x values that are larger than -3. And then for our range, since we're going forever up and down, we have all real numbers.